Hi, everybody. Welcome back to Are We on the Same Page? And this is my fourth video in my series on the history of invention. And today I'm up to the Renaissance. That's the fourth era of human history, fourth out of six that I'm going to talk about. And today I'm going to count down what I consider the top 20 inventions of the Renaissance, which I'm defining to be between the years 1500 and 1749. I don't think there's any clear years for the beginning or the end of the Renaissance. I just kind of defined it this way. I'll go over that in a minute. But anyway, before I begin, I want to give a plug for my book again called My Spiritual Journey. This is available both in Kindle and in paperback on Amazon. You can just go to Amazon.com and search for my pen name, Dave Thomas Rocker. And the book is called My Spiritual Journey, and I think you'll enjoy it. I think it's a good book. I think you'll get a lot out of it. It's kind of an enjoyable. It's not very long. It's about 100 pages. And it's mostly one-line quotes about how I think you can live a good life. So, anyway, check it out. And you may disagree with me on some of my quotes. You probably will. I'm not trying to just appeal to everybody. I'm trying to state what I think works for me, and it may not work for you, but you can be the judge of that yourself. Anyway, so that's a plug for my book, and now I'm gonna begin my video for today. And before I count down the top 20 inventions of the Renaissance, I'm gonna briefly talk about the different eras of human history. I've divided human history into these six eras, and I've already done videos on the first three of these eras. I 3 weeks ago I made my first video in this series. I counted down the top 10, what I consider the top 10 inventions of the Stone Age, which I'm defining as being between roughly 5 million BC and 10,000 BC. This is basically primitive man before what we would call civilization, which really began with the Neolithic Revolution, which was the beginning of agriculture. And then the second era, which I'm calling ancient times, that spans, according to my definition, from 10,000 BC to 500 AD. And this encompassed all the ancient civilizations that I'm sure you guys are all familiar with: ancient Egypt, ancient Greece, ancient Rome, all that. And in that one, I counted down the top 20 inventions. And then last week I did one on the Middle Ages, also called the medieval era, that I'm defining as between 580 and 1499. And I only did 10 inventions for that era because there wasn't a lot of invention during the Middle Ages. It's also known as the Dark Ages, and I think for a lot of good reasons. But I did talk about 10 pretty great inventions from that era. And the next 3 years, I'm going to do 20 inventions for each of these eras because each of these eras did involve a lot of invention and innovation. In particular, the one I'm going to do today, the Renaissance, which is from 1500 to 1749. And then the last two are going to be next week. I'll do the Industrial Revolution, which defining between 1750 and 1899, and finally the modern era, which I'm saying was from 1900 to 2024. I started this series at the end of last year, which was still 2024, and it's still early in 2025. And as far as I know, there haven't been any great inventions so far this year, so I think I'm safe on that. Anyway, so let's just get started with today's videos on the what I consider the 20 greatest inventions of the Renaissance. So number 20 on my list is the slide rule. And I don't even know how many of you guys are familiar with a slide rule, but I used to use these things, and I loved them when I was a kid. I mean, this was a very important mathematical tool for a couple hundred years. I mean, before the pocket calculator, it was really the pocket calculator that made the slide rule obsolete. I'd say during the early 70s. I mean, the first time I saw pocket calculator, I think the first ones that were commercially available were in 1971. I was just 9 years old at the time. But there were people still using slide rules at that time. And let me just tell you a little bit about slide rule first. So the first slide rule was made in 1622, and it was invented by an Englishman, I believe. Yeah, Outred. I don't know if yeah, William Outred. He made the first slide rule in 1622. And what a slide rule is, in case you guys aren't familiar with these things, it looks a little like a ruler, but it has a thing in the middle that slides, since its name, and it has these scales on it. How well you can see this, but there's all these different measurement scales or number scales, and the simplest operation you can do with a slide rule is multiplication or division. And it's pretty clever how these are designed, because they use a logarithmic scale, which basically allows you to multiply by adding or divide by subtracting. And it's an analog device, meaning you just slide the rule in the middle, and then there's a kind of an indicator, this little window thing you can move back and forth. So, for instance, if you wanted to multiply, say, 2 times 3, you would line up the little hair on the window to the 2 on the on the top and the bottom, and then you'd move the middle rule distance 3, or you'd move it so that the 3 on the outside lines up with a 1 on the inside, and then you see where the thing matches up, and the hair should indicate a 6, which is the product. So that's kind of how it works. That's the simplest operation you can do with a slide rule. And just by doing that in reverse, you can divide. And then there's a lot of other scales you can use. I mean, this is a pretty complicated slide rule shown here. Showing both the front and the back. And, there's scientific slide rules with a bunch of different types of insets in the middle you can put in, each of which do different kinds of scientific calculations. So you can do things like all the trig functions, sine, cosine, tangent. You can also do logarithms and exponents. You can basically do all the calculations you can do with a calculator. The disadvantage is it's analog, it's not digital. So you don't get the same kind of precision as you do with a calculator. You can't, the best you can do with a slide rule is maybe 3 or 4 digits precision, which is usually good enough for most scientific or engineering purposes. But sometimes you want an exact answer, and that's why pocket calculators are much better, and they're also a lot easier to use. So anyway, that was slide rules, a very important mathematical innovation, I think. And number 19, a pocket watch. These aren't used anymore. These are obsolete, but these were used for a long time. I'd say about 200 years or so. And unfortunately, they were pretty expensive, so they weren't just used by common people. They were mostly used by rich people who could afford them. But the first pocket watch, I don't know if you'd really call it a pocket watch, but the thing on the left, this was I guess a handheld time measuring device. It doesn't really look like a pocket watch from today, but you could tell the time with it. And this was built in 1505 by the German inventor Peter Heinlein. So that was the first pocket watch on the left, on the bottom left. And a more modern pocket watch is the one on the bottom right. This one was from 1924. It was known as, what's the name of that type of watch? Save-A-Net. And there used to be some pretty fancy pocket watches. They'd have a little stopwatch feature, the thing on the bottom. You could do a lot of fancy stuff with these watches. And they were the reason, I think another reason they were really important, besides being a portable time measuring device, was that they led to the invention of the wristwatch by the mid 20th century. And these were very common. I mean, pretty much everybody could afford a wristwatch. I've had wristwatches most of my life, and the early ones, the ones I had as a kid, were all wind up. I don't know how many of you guys remember wind up watches. I mean, the pocket watches, you had to wind them up. They used a spring. They were mechanical. And nowadays, of course, all pocket watches are electrical. They use a quartz, quartz crystal that keeps really, really accurate time. They're much more accurate than the old spring, watches. So Anyway, but that was a pocket watch, a very important invention for a very long time. And number 18, the stocking frame. This was, I think, the first mechanical device for making fabrics. And I think last week I featured the the spinning wheel, which was a handheld device, just a device that was used by individuals in the home. Well, the stocking frame marked a big kind of revolution from that because it allowed for mass production. It was the first thing that kind of allowed for mass production of textiles and fabrics. And of course, this led to, some bigger inventions later on, like power loom and all that. But it was a beginning in the industrialization of textile production, and the first stocking frame was built in 1589. There's a picture of a model of it on the right, and the inventor was I can't remember who the inventor was. Oh, he was an English clergyman named William Lee. Um, so anyway, that's the stocking frame. Number 17, the Franklin stove. This was one of many really innovative inventions by very famous man, Benjamin Franklin. I'm sure you guys have all heard of him. He's on the $100 bill. And he was, one of the most famous Americans in our history. He was one of our founding fathers, and he was also a great scientist and inventor, really a polymath. And one of his inventions was what's now called the Franklin stove. And he invented that in 1742. And the Franklin stove was, an innovation in it was a type of fireplace, basically, but it was a very well designed fireplace, and you can see a schematic of it on the bottom right. What it did was it kind of you had a fireplace where you'd light a fire, and then the fire would heat this air, but it would heat it from above. So you'd have hot air, below the fire, and then you'd have this kind of inverted pipe, and so the hot air would rise through it, and it was a lot cleaner than the older fireplaces, which put a lot of soot in the air. So it really did mark and it was also more efficient. It created more heat. So not only was it a more efficient way to heat your home, but it was also a lot cleaner. So that was a pretty important invention. Um, and I guess it just barely made what I'm calling a Renaissance, 1742, because I'm defining it up to 1749. And number 16, this was a big one, the reflecting telescope. And this was invented by a very, very famous polymath. I'm sure you guys have all heard of him, Sir Isaac Newton. Probably, he's usually considered the greatest scientist of all time, or at least the greatest physicist of all time. Amazing man. And one of his amazing accomplishments was his invention of the reflecting telescope. And this wasn't the first optical telescope. I'm going to get to that one later on my list. That was the refracting telescope. Came earlier, I think 1608. So about 60 years after the first optical telescope was made, Isaac Newton made this improvement called the reflecting telescope. And as the name implies, the reflecting telescope, instead of using lenses, which is what the refracting telescope uses, reflecting telescope uses mirrors. And there's a lot of advantages of using mirrors versus lenses. For one thing, if you're building a really big telescope, with lenses, you'd have to have really big lenses, and it's not practical to make huge lenses. I think the biggest refracting telescope ever built, I believe, was a 100-inch telescope. I think it was built in the 1920s. I think it's the one over at the Griffith Observatory in Los Angeles, if I'm not mistaken. Um, has a big, huge lens in it. I've actually looked through it. It's pretty amazing. But reflecting telescopes, you don't need nearly as much equipment to build them. And, another problem with refracting telescopes is that, you get this thing called aberration. I didn't talk about that here in this slide, but you get chromatic aberration and you get blurriness based on, you have to make the lens perfectly, or you have to make a lot of corrections for lenses with big telescopes. But with mirrors, it's not so critical. I mean, you don't get chromatic aberration with mirrors for one thing. You get other kinds of aberration, but they're easier to fix. And the mirrors don't have to be so big and so heavy as the lenses. And as a result, the biggest optical telescopes in the world are all reflecting telescopes. The biggest ground-based reflecting telescope, which I think is also the biggest reflecting telescope, is the one shown on the bottom right. By the way, the picture on the top right is a model of Newton's originally reflecting telescope, which kind of looks the same as most, amateur reflecting telescopes today. This one on the bottom is a 410-inch or 10.4-meter reflecting telescope. It's a huge thing, so like 30 feet wide, huge. And This is in Spain, I believe. Yeah, it's called the Gran Telescopio Carnarius, or GTC. And the probably the most famous reflecting telescope in the world, and I think the one that's given us the best astronomical observations, is the Hubble. I'm sure you guys are all familiar with the Hubble Space Telescope. This was built, I think, in 1993, or at least perfected then. When they originally designed it, they made some mistakes. They had to correct some of the optics, but I think they finally got it working properly in 1993, and has brought back some amazing pictures of some of the most distant known objects in the universe, uh, almost going back as far as the Big Bang. So, that's reflecting telescopes for you. And number 15, the pencil. I don't think any of us can doubt that the pencil was a very important invention. I mean, most of us, I think, still use pencils, or at least we used them when we were kids in school. And the biggest advantages, I'm sure you guys all know, that pencils have over other writing instruments, namely pens, is that pencils are erasable. I mean, there are erasable pens now, but it's a lot easier to erase with pencils, and pencils are a lot cheaper. And they used to have lead in the middle, which was poisonous. So I don't know when, probably during the 1950s. Anyway, I think it was before I was born. They replaced lead in pencils with graphite, which is not poisonous. It's just a form of carbon. So you can chew on pencils. Kids can lick the graphite and not get poisoned. I mean, we all know about pencils. They're very useful. And not just the standard pencils used in school, but, they're used for art too. I mean, here's a picture on the bottom showing all these different colored pencils. Artists use a lot of colored pencils to make some beautiful sketches. And so that's pencils. We can't deny their importance. And the pencil was invented in 1560 by a couple. It was Hyman. Maybe it wasn't. No, that was an improvement. Yeah, it was a couple. It wasn't. Um, yeah, Simon and Lydiana Benicati. I guess they were an Italian couple. And the first pencil with eraser wasn't made until 1838 by Hyman Littman. I don't think pencils were in widespread use until the mid 19th century. But anyway, it was a very important invention. And number 14, the piano. I don't think we can deny the importance of the piano. I mean, one of the greatest instruments in the world, musical instruments, probably the most versatile instrument. I've been told that the piano is the best instrument for anybody to learn who wants to learn to play an instrument, because for one thing, once you learn to play the piano, you can pretty much learn to play any other instrument. You have to kind of learn how to read music for the piano, but then music for the piano is the same music you use for all other instruments. And you can compose with pianos. You can play beautiful songs. You can play pretty much any kind of music on a piano. And my mom almost became a concert pianist. My mom is one of the best pianists I know. I'm not a good pianist myself. I have played the piano. I've also played the electronic keyboard. You know, but it usually takes me several months to learn how to play a song on the piano because I have to read the music first, and I kind of have to memorize the music. I can't really look at my fingers and look at the music at the same time. It doesn't come so natural to me. But for my mom, she could just hear a song and without even looking at any music, play it on the piano. And I know very few people who can do that. That's an amazing skill that I've never had. So kudos to my mom for being able to do that, but it's not a skill I have. But we can't deny the importance of the piano. And the first piano was built by Bartolomeo Cristofori. I guess he was Italian in 1709. I think it was an offshoot of the harpsichord, which was used in the 17th century and I guess early 18th century. And there's different types of piano. There's grand. I guess the one shown here is an example of a grand piano, but there's also upright pianos, and pianos are very well designed, for acoustics and all that. And they're pretty complicated instruments, but they have beautiful sounds. So that's piano. And number 13, this is one I really like. This is the adding machine. And some people call this the mechanical calculator. I don't like to call it that because this was the first mechanical calculator. It's also known as the Pascaline. It was invented by a very famous French mathematician and physicist named Blaise Pascal in 1642. And you can see what it looks like. There's a picture of it on the bottom here. And this model had six. It used decimal digits, and I think you can kind of see the display of the digits. It's on the top of the top face. There's six little square holes that have digits 0 through 9. I don't think you can really see the digits, but they were written on these things. And then there's these little wheels or rotaries, I guess. Below the numbers, and there's a stylus that you can use to rotate these wheels, a certain number of positions, kind of like you used to do with the old telephones. I remember the rotary telephones when I was a kid, which are hardly used anymore. But it had the same kind of rotary dial as the old rotary telephones. And what you would do was you would first enter a number. You rotate with the stylus so you could enter any number up to, in this case, 6 digits. And then if you want to add another number with up to 6 digits, you just use a stylus to rotate an additional number of digits. So you just enter the second number. And then this thing would do all the carries, all the necessary carries, and it would display the result of the sum of the two numbers. And you can use it for subtracting too, just go the other way around. So that was the first adding machine, and you could use it to multiply or divide, but it was a lot harder to do that. You had to multiply by repeated addition, and it took a long time to do that, and you could, I guess, divide by repeated subtraction, but it wasn't so easy to do that. But you could do it if you wanted to. And there were later mechanical calculators that were more sophisticated than the Pascaline. I believe Leibniz, who I'm going to get to later, he invented a calculating machine in the 18th century that could multiply and divide with one step. Not only that, I think it could also compute square roots. And it was a mechanical device. So there were some pretty amazing mechanical calculating devices way before, computers and pocket calculators, which is pretty amazing to me. And the Pascaline was, I guess, the first of those. So anyway, number 12, the newspaper. I don't think any of us can deny the importance of newspapers. I mean, they're hardly used anymore, at least in, I guess, the developed world, because now everybody has cell phones, smartphones, and PCs. So you can just get on the web and look up the news, or you can watch the news on TV. There's thousands of news channels. So you can get whatever news information or disinformation, misinformation you want on the web these days. But in the old days, and it wasn't even that long ago, I think until maybe just about 20 years ago, just about everybody in the world was using newspapers to get their news information. And the first newspaper was published in 1609, and it was known as the Relation. It was a German publication by Johann Carolus, and the first copy of the Relation came out in 1609, and here's a picture of it. So that was newspapers. And anyway, number 11, the vacuum pump. This is a pretty amazing invention, I think. So the principle of the vacuum, this is part of the scientific revolution. I mean, Aristotle was wrong about vacuums. He said nature abhors a vacuum. I think Aristotle taught, and people believe this for about almost 2,000 years, that we couldn't have a vacuum in on Earth. There was vacuum in space maybe, but a vacuum wasn't possible on Earth because he said nature abhorred a vacuum. Well, that's not true. I think one of the first people to actually make a physical vacuum on Earth was this guy who invented the vacuum pump. He was a German scientist named Otto von Guericke. And what he did, this was in 1650, he came up with this spherical device that consisted of two hemispheres, as you can see in the picture on top. So there was two big metal hemispheres, hollow hemispheres. You'd put them together, and then you'd pump all the air out of the middle. You create a vacuum inside. You just pump, as much air as you could get out, and you could get pretty much all the air out if you did it hard enough. And the amazing thing about that, he also discovered the principle of air pressure when he did this, because what happened was he discovered that once you created a vacuum inside this sphere, you couldn't pull these hemispheres apart anymore. There was too much force, pulling them together because of the vacuum inside. What was really going on was that, the air has a lot of pressure. And so was the air pressure outside the sphere that was pressing on the two hemispheres. And I don't know if you guys realize, but the standard air pressure at sea level is about 15 pounds per square inch. So, if these I think for this particular sphere he made, the total amount of force you needed to separate these hemispheres, I did this calculation once. I think it was around 6,000 pounds, about 3 tons. And he actually did an experiment. He did a demonstration where he took two teams of horses and he had them try to pull apart this sphere that had a vacuum inside. And they couldn't do it. These two teams of horses could not pull apart these two hemispheres. That was a pretty dramatic demonstration of the power of the vacuum. So that was the vacuum pump, which was kind of the first practical use of a vacuum. Of course, now we have vacuum cleaners we all use to clean our carpets, and there's industrial vacuum cleaners for cleaning more, doing more rigorous cleaning. I'm sure you guys all know about how useful vacuums are. So anyway, that was the beginning of all that. And then number 10, this is another device that relies on a vacuum, the barometer. And the barometer is a very important meteorological instrument. It measures air pressure. So, vacuum, the last invention, the vacuum pump kind of demonstrates the practicality of the vacuum. But, I guess this is another demonstration of its practicality, but this is a different kind of demonstration. This is a measuring device called a barometer. And this was invented by an Italian scientist named Torricelli in 1643. And it's actually a pretty simple device. What you do is you start with a big bath of mercury. Mercury is a very heavy liquid metal, as I'm sure you guys all know. It has a density, I think, of 13, specific gravity of 13.6, which means it's about 13.6 times as dense as water. So it's a very dense liquid. And, the density turns out to be a very important property in the barometer. This would not work very well with water. So what happens is you have this big vat of mercury, and then you take this big long tube, kind of like a test tube. What you do is you dip this tube. You start by dipping this tube completely inside this bath of mercury, and if you do that, when you pull out the tube, what you'll find is that the mercury will rise. It doesn't just stay level when you pull it out of the mercury from the source. It actually rises, and this tube has to be pretty long. I mean, the tube has to be at least 30 inches long, or in metric about 80 centimeters long. Because what happens is when you pull it out of the water, I mean out of the mercury, at least 76 centimeters, you'll find that the mercury on top, it'll stop. It rises. It doesn't rise indefinitely. It only rises to about 76 centimeters above the level of the mercury in the dish. And the reason it does is because it's equalizing the pressure. See, there's air pressure pressing down on the mercury in the source. And then there's also pressure from the column of mercury. The pressures have to be equal. The total amount of force on the mercury has to be equal, or the amount of pressure on the mercury has to equal the pressure on from the air. And what that really means is that this column of mercury inside this tube, which is 76 centimeters tall, or about 30 inches tall, about 2.5 feet tall, the weight of that column of mercury, which is pretty heavy because, like I said, mercury is a very dense liquid. The weight of that column of mercury is equal to the weight of a column of air of the same width, the same size, or the same dimensions, if you like, but going all the way up through the whole atmosphere, the whole Earth's atmosphere. So that's what that means. And of course, we know that the pressure of the atmosphere decreases as you go up. There's what's called the scale height of the Earth's atmosphere, which is about 5 miles or 8 kilometers. That means if the Earth's atmosphere had the same density as it does at sea level, which it doesn't, but if it did, then the atmosphere would only get up to about 5 miles or 8 kilometers. So what that means is this 30-inch column of mercury has the same weight as a column of air of the same width and a height of about 5 miles. I mean, that just shows you how much heavier the mercury is than air at sea level. But that's the principle of the barometer. And the reason this is a useful device is because the air pressure at sea level is not constant, as you probably know. It's approximately constant, but it can go up or down. And depending on how far it goes up or down, that kind of tells you, that kind of can be used to predict the weather a little bit. I mean, if the pressure is low, you probably know that low pressure means that you're going to get a lot of clouds coming in. Usually, low pressure is a sign that there's an incoming storm. You're probably going to have a rainstorm if you have low pressure. If the pressure is like, they used to do this in inches. If the pressure was 29 inches, that's low pressure. I think normal is about 30 inches, or 760 millimeters. A torr, by the way, is air pressure unit equal to 1 millimeter of mercury. What's called a standard atmospheric pressure is 760 torr. It's the pressure that would make this column of mercury rise to a height of 760 millimeters, or 76 centimeters, if you like. And that's normal, that's standard atmospheric pressure, which in inches, I believe, is 29.92. But, like I said, if it's lower than that, it means you're probably going to get a lot of clouds coming in. If it's higher than that, they say that's fair weather. That means it's going to be clear. So you can kind of tell what the weather's going to do just based on the air pressure, and that's what makes it really useful in terms of meteorology. And it's also really useful. I think it's even more useful in terms of flight. I mean, I took flying lessons for a couple of years, and one thing you have to know if you're learning how to fly an airplane, you have to become an expert at meteorology. And what you always have to do before you take off is you have to radio the tower. You have to tell them, or they tell you what the air pressure is. You have to go on the radio and you have to listen to the radio broadcast, and they'll tell you what the air pressure is where at your airport. And the reason you have to know that is you have to enter it into the instruments on your airplane because they all rely on the air pressure. And they wouldn't tell you the right. They tell you what your altitude is. It's mainly for the altitude because you have to calibrate the altimeter on the airplane according to what the air pressure is. Otherwise, you'll get the wrong reading. That's how they measure air pressure. At least in the plane I was flying. I think most planes still do that. I flew a Piper Cherokee that was built in 1969, and it relied on instruments that relied on air pressure. So that was a very important application of a barometer that measures air pressure. And I guess one more thing I want to say about this, you also get a vacuum when you do this. If you lift this column, like I said, over 76 centimeters, you're going to get a region on top that has a vacuum in it. That's what's known as a Torricelli vacuum. And one thing that's kind of remarkable about this is it doesn't matter if you tip the tube, you're still going to get the same height for the column. And you could even make the vacuum go away. You can, if you tip it far enough so that the top is less than 76 centimeters above the level of the mercury, then there's no more vacuum anymore. So, pretty neat device, I think. And I used to see it demonstrated when I was studying physics as an undergrad. Anyway, that's a barometer. Number 9, another meteorological device, the thermometer. And I think you guys are all familiar with thermometers. They tell you the temperature. And the first thermometer was made in 1612, and it used water. It was the guy who invented the first um, um, thermometer was Italian polymath named Santorio Santori, and it's basically the same as the modern mercury thermometers. Just he didn't use mercury; he used water, which wasn't very practical. But same principle. You heat water, it expands. You heat pretty much any liquid, and it expands. And that's the principle behind a thermometer. And modern thermometers, most thermometers use mercury. Mercury is a very good liquid to use. For one thing, it's very dense, like I said. For another thing, it has a very regular, rate of expansion in terms of temperature. And it also freezes at a very low temperature. I think you guys all know, water freezes at 32 degrees Fahrenheit or 0 degrees Celsius, which isn't really that cold. A lot of places in the world get colder than that, including where I live here, Las Vegas. Sometimes it does go below 0 degrees Celsius. And so, you would want a thermometer that goes below that, obviously. And mercury thermometers you can use for as low temperatures as minus 40 degrees, which coincidentally is the same. It's the only reading that's the same in Fahrenheit and Celsius. Minus 40 degrees Fahrenheit and minus 40 degrees Celsius are the same temperature. And they're also approximately the temperature at which mercury freezes. That's why they're the lowest temperature you can measure with a mercury thermometer. You'll never see a mercury thermometer that blows below minus 40 degrees. But they're very useful, as you guys all know. And I think pretty much most thermometers, at least most meteorological thermometers that measure the air temperature are mercury thermometers, as far as I know. And there's also alcohol thermometers. They used people. I know that. I remember when I was a kid, you used to have to stick a thermometer in your mouth if you were sick, to measure your body temperature. I think now we have electronic thermometers that do that a lot more easily. But I think those had alcohol in them. You wouldn't want to put a mercury thermometer in your mouth because if it broke, mercury is poisonous and that could kill you. So they would use alcohol for those, and same principle with alcohol too. And anyway, that's thermometers. And, I don't think we can deny the importance of thermometers, not just for measuring, not just for the weather, but for measuring temperatures on stoves and ovens and, forges and all this other things. There's a lot of times we want to measure temperatures, so we have to use thermometers for that, different kinds of thermometers, not just mercury thermometers. But anyway. That's thermometers. And number 8, the submarine. You guys might be surprised that the submarine was a Renaissance invention. I was pretty surprised when I learned this myself. But the first submarine, the first submersible, boat or ship, I don't know what they called it, but submersible craft, which is also called a submarine, was built in 1620 by Dutch engineer and inventor Cornelius Drebbel. And there's a picture of it on the bottom left, a little illustration of the first submarine. I don't think it could go very deep. I mean, one thing you have to realize about submarines is that when you're going underwater, depending on how far underwater you go, the pressure can rise very, very fast. I mean, the water pressure is the same principle as air pressure. Water pressure, like I said, air pressure, it gets higher the lower you are. It's highest at sea level. It's a lot lower when you go to high altitudes because there's less air above you. Same principle about water. So water pressure is really the weight of all the water above you. And water pressure increases about 30 psi or pounds per square inch for every what is it? I have to get this right. It increases about 1 atmosphere, which is 15 psi, for every 30 feet you go down. It increases about a half a psi for every foot you go down. I prefer to think in metrics. So for every 10 meters you go down, the water pressure increases about 1 atmosphere. And I don't know how many guys know about the Titan disaster a couple of years ago. There was a really crazy guy named Talk Rush. He was actually a classmate of mine. I hated that guy, and I don't really feel sorry for him. But what happened was that he piloted, or he was the captain of this tiny submarine called the Titan. It was only about 20 feet long and about 7 feet in diameter, and he went all the way to the bottom of the Atlantic Ocean with this thing, which was like 12,000 feet deep. And the pressure, or about 3,200 meters, the pressure at that depth is about 300 atmospheres. And this Titan submarine could not withstand that pressure, so it imploded. And not only he died, but he took 4 billionaires along with him. And he violated all the regulations that the engineers had put in place for this Titan submarine. I made a video about this on my math channel, by the way. And I don't feel sorry for him. I guess I feel a little bit sorry for the billionaires he took aboard this thing, you know. But he knew damn well what he was doing, and he knew he was violating the regulations. And not only did he kill himself, but he killed the 4 passengers that he took aboard this thing. So, you know, I think he got what he deserved. I don't usually say that about people who died, but in this case, I do think so. Also, he was a real asshole to me when I knew him in elementary school, so I don't have any good feelings about him from the past. But anyway, enough about him. What else do I want to say about submarines? Well, I think you guys all know that submarines have been used for warfare. Particular starting in the 20th century. I mean, the first horrible military submarines were the U-boats that were built by the Germans, first used in World War One and later in World War Two. And they were horrible. Submarines that killed a lot of people at sea, and You know, fortunately, we were able to win World War II. But then after World War II, during the Cold War, as I'm sure you guys all know, nuclear submarines started being used. I think the first nuclear submarine was the Nautilus. I think this was made just probably, I think it was like 1946. I don't remember what year the Nautilus was built, but I think it was almost right after World War II. And it was the world's first nuclear submarine. And nuclear submarines use nuclear power, as a form of locomotion. They have a nuclear power plant inside, or nuclear reactor inside that gives them power. Not only that, but a lot of them carry nuclear weapons as well. So I think they're very, very scary submarines. Unfortunately, nobody's ever launched a nuclear weapon out of a submarine before. I hope we never do. I wouldn't put it past Trump, unfortunately. But so I'm not happy with nuclear submarines. I did have a friend in college who was in the Navy ROTC, and he even had a mission aboard a nuclear submarine. I even visited him when I was in college. He was my best friend in college, and he came to visit me. It was kind of a funny story, actually. Before I get off this, might as well tell a funny story. This was back in 1981, I believe. I started college at the University of Michigan in 1980. I met this guy's name was Bruce. He lived right across the hall from me, where I was going to school in Ann Arbor. And I think it was over Christmas time, he came to visit me. I lived in San Francisco, and he was stationed in Alameda, I think. And I guess he had an assignment from the Navy ROTC to go on board a nuclear submarine out of Alameda, and so he came into the San Francisco harbor to meet me, and I was trying to tell this to my parents. I remember, my parents knew he was coming to visit me. This was over Christmas vacation. They didn't know when he was coming or what, and I remember my dad woke me up. It was like 8 in the morning, and he asked me, what time is your friend flying in? He thought he was flying in to meet me. And I said he's not flying in. I said he's coming in on a submarine. And I had just woken up, so I couldn't explain to him in detail what was going on. My dad just thought I was delusional and dreaming. Maybe I was thinking about the Yellow Submarine by the Beatles or something. But anyway, then my dad got a call that afternoon from my friend. Said, "Oh, I'm in Alameda. I just came in on my nuclear sub. I'm stationed in Alameda." So then my parents knew I was telling the truth, and they knew what I meant. It was kind of a funny story. But anyway, I even went on the nuclear sub. I went into the submarine. I got to see it firsthand. It was pretty cool equipment inside. It looked kind of like what they showed in the movie The Hunt for Red October. I don't know how many guys saw that movie. They had pretty sophisticated equipment aboard these nuclear subs, and I'm sure it's even more sophisticated today, but I just kind of wish we didn't have them because, I'm pretty scared about nuclear weapons in general, including those used aboard nuclear subs. So, anyway, that's submarines. Not my favorite invention on this list, but number 7, the pendulum clock. I think this was a pretty great invention. This marked a real revolution in timekeeping. And the principle of the pendulum clock is actually very simple. And it was discovered by a very famous scientist I'm sure you guys have all heard of, Galileo. Galileo Galilei. He's considered the father of modern science. When he was 17 years old, this was back in 1581, he was at a church. I guess his parents used to go to church like everybody else did. And there was an earthquake. And there was a big chandelier in this church. And the chandelier started rocking, back and forth, swinging. And, being the scientist he was, I guess he was bored. He decided to try to measure the period of oscillation of the chandelier in the church, and he measured it with his pulse, since there were no accurate clocks at that time. He measured how many heartbeats he had each time the chandelier rocked back and forth. And what he discovered was that as the amplitude died down, as it started swinging not so hard, its period stayed the same. So Galileo basically discovered the principle of the pendulum at age 17, which is basically that the period of a pendulum doesn't depend, at least the first order, it doesn't depend on the amplitude of vibration. And this is the principle behind the pendulum clock. The guy who invented the pendulum clock was another very famous physicist named Christian Huygens. He was a Dutch physicist and polymath, and he made the first pendulum clock in 1656. And I'm sure you guys have all seen pendulum clocks. I mean, grandfather clocks are examples of pendulum clocks. They have a pendulum that rocks back and forth. That usually ticks. It makes the clock tick as it's rocking back and forth. And the reason they're so accurate is because the period, like I said, doesn't depend on the amplitude. So it doesn't really matter how hard this thing rocks back and forth. And usually it does rock back and forth at pretty close to the same amplitude. It also uses a weight. It's kind of like the mechanical clock, but it also involves a pendulum. And the pendulum gives it really good regularity. So pendulum clock marked a big revolution in timekeeping, because whereas the older mechanical clocks, which was a late medieval invention, those were the most accurate clocks of the Middle Ages. Those were okay for the time. I mean, those would keep time to within about a minute accuracy per day, which was pretty good for the time. I mean, you had to keep resetting them when they got off, obviously. But pendulum clocks were much, much more accurate. They were accurate to within about a second a day. And they were so accurate, that they were used for railroads. They were used for, very practical timekeeping for a really long time. For a couple of centuries anyway. And the first clocks that kind of made them obsolete were electric clocks. This is by the 1930s. Once electric clocks, that ran on AC, once those became in widespread use, those were much more regular because they relied on the 60 hertz AC, Uh, but but until then, the pendulum clocks were the most precise clocks in the world. So pendulum clock was a big revolution in timekeeping. Because disadvantage of pendulum clocks is, yeah, they have to be stationary. Most of them have to be stationary because if you're moving or accelerating, they don't work so well. The pendulum does weird stuff it's not supposed to. And one of the challenges, I'm getting a little sidetracked here, but a big challenge for navigators during the 18th century was to try to build a reliable portable clock that could be used to see. I think they called it a chronometer. And it wasn't built until I think 1760, around then, mid 18th century sometime. Before then, and the reason that was a really important invention was because I might get this Industrial Revolution inventions. I'm not sure. I think it was during the early part of the Industrial Revolution, but the reason that was a really important invention was because that was the first that was necessary in order to determine longitude at sea. The only way you could reliably measure your longitude at sea was to have a really accurate timekeeping device aboard your ship. And until we had them, we couldn't really determine our longitude at sea. It was very easy to get lost at sea. But anyway, that's kind of a digression. Anyway, that's pendulum clocks. And number 6, this is one I really like, and I don't know where we'd be without this. I think it's pretty obvious that we all need flush toilets, and I'm just going to read this for because I think it's pretty good what I say here. So where would we be without toilets? Flush toilets in particular. No doubt, the flush toilet was a critical invention. The first flush toilet, a model of which is shown on the right, was invented and built by Britain's Queen Elizabeth II for Britain's Queen Elizabeth II by her godson, Sir John Harrington, in 1596. Today, flush toilets are in widespread use throughout the developed world. Its main importance is that it has led to a vast improvement in sanitation in modern society, which has significantly improved our health, longevity, and our overall well-being. So I don't think any of us can doubt the importance of the flush toilet. I'm just really glad we have them, and I wouldn't really want to imagine living in a world without them, even though I think there are a lot of poor parts of the world that don't have them. Anyway, I'm glad we have them here. Number 5, the microscope. This, I think, was a really great invention. I mean, think about it. I mean, microscope, obviously that marked a real revolution in experimental science. It allowed us to see microscopic objects, in particular, like bacteria and amoeba and cells. It started a revolution in biology. Pretty obvious to see. I mean, you just look through some really tiny thing through the eyepiece of a microscope. You could look at things that are like 1,000 or 10,000. I think you could go up to maybe 100,000 x. I don't know what the. I mean, optical microscopes are limited by the wavelength of light. You can't see objects that are smaller than about the wavelength of light, which is about 500 nanometers, which is pretty small. But it's smaller than a bacteria, but it's bigger than a molecule, or at least most molecules. So you can't see molecules with optical microscope. You can with electron microscope, and you can see a lot more detail. I mean, you can't really see, I think, viruses with an optical microscope either, or at least you can't see them in detail. But with electron, the way electron microscopes, I'm getting a little digression here. The way electron microscopes work, and these weren't invented until the 1930s, but these use wave properties of electrons. It turns out it was de Broglie. He was one of the pioneers of quantum mechanics. He discovered that matter has wave properties, just like light. And so you could use electrons, which is a form of matter. You could use them, the wave properties, to observe really small objects in the same way as you can use optical microscopes with light. And you could, electrons have a much shorter wavelength, or you can make them have a much shorter wavelength, which is why you can observe things that are a lot smaller with an electron microscope than you can with an optical microscope. But nobody could observe an atom, and this really surprised me for a long time. I remember learning this as a kid. Nobody saw an atom until the 1980s. I remember hearing that a lot as a kid in the 1970s when I was in school and learning science. We knew all this stuff about atoms. I mean, we were even able to split atoms. We knew atoms inside out. We knew all the parts inside of them: electrons, protons, and neutrons, the nucleus, the nuclear shells. The whole basis for chemistry and the periodic table. We knew all that. We even knew the size of all these different atoms, but nobody had even ever seen one. And I always wondered as a kid, how is that possible? How can we know so much about atoms if we've never seen one? But obviously it was because we deduced a lot through other areas of science. I learned that much later. But now we actually have seen atoms, and the way we've been able to see atoms, and we can even move them around too, with the same device. There's a thing called a scanning tunneling microscope that was invented in the 1980s, and it relies on another property of quantum mechanics called tunneling. It creates this tunneling current, which you scan over usually a surface of a metal or some material, and depending on the current, the current is a function of the gap, kind of the gap between the tip of the scanning tunneling microscope (STM) and the surface that you're looking at. So it kind of moves in and out according to whether or not there's an atom on the surface. And so you can actually make pictures of the atoms on the surface of a material. And I've seen these pictures, they're pretty amazing. So we've seen atoms now. with the most powerful microscopes in the world, unless you could argue that particle accelerators are more powerful microscopes. I don't think of those as microscopes. I think of those as, just kind of, you can smash together particles. I mean, we could probe distances a lot smaller than atoms. We can probe distances down to about 10 to the minus 18 meters, which is about 1,000 times smaller than a proton. I mean, a proton itself is about 100,000 times smaller than an atom. We can see atoms. We still can't see protons, but we can probe distances that are 1,000 times smaller than protons with high energy particle accelerators, which I don't think of as microscopes. But I guess that's kind of open to debate. Anyway, that's a microscope. I got sidetracked as usual. Uh, Number four, kind of the opposite of the microscope, the telescope. Just like a microscope allows us to peer inward, telescope allows us to peer out. And, I guess I put telescope above microscope. Maybe that was a personal choice. I'm not that. I've never been all that crazy about biology. Never studied that much of it. Maybe if I was a biologist or a doctor, I'd probably prefer microscopes. But since I like astronomy better than biology or medicine, I guess I prefer telescopes. But we can't argue that they're both important. And uh, the first telescope was invented in 1608. We don't know who built the first telescope, but the guy who got credit for patenting the telescope was a Dutch lens maker named Johann Lippershey. I don't know how to pronounce it. Lippershey in 1608. Here's a picture of him on the right looking through one of his telescopes. But the guy who really made telescopes most famous, I think, was Galileo again. Galileo Galilei, the father of modern science. He built his own telescope. He improved on Lippershey's telescope because I guess Lippershey's telescope wasn't powerful enough for him, so he made an even more powerful telescope. I think Galileo's telescope was about 30x magnification about power 30. That allowed him to see things that nobody had ever seen before. I mean, I think you guys all know about Galileo. He pretty much turned the world upside, at least astronomy upside down with his observations of the solar system. First, he observed craters on the moon. Pretty much everything he observed about the solar system contradicted just about everything that had been taught for the past 2,000 years before. Since Ptolemy. I mean, Ptolemy had this book called the Almagest, which was kind of the Bible of astronomy, and it assumed the Earth was the center of the universe because, of course, that's what the church wanted everybody to believe. It turned out it wasn't, and I think it was first Copernicus who suggested the sun was the center. He didn't have a telescope to verify that, but Galileo used his telescope. One thing he observed phases of Mercury and Venus, which proved that the sun was the center of the solar system rather than the Earth. That Venus and Mercury were closer to the sun than the Earth was. That's the only way you could have phases on those planets. And then he also observed craters on the moon, which meant the moon wasn't a perfect sphere, as that was another dogma that the church was promoting. And also that Jupiter had four moons of its own. They're known as Galilean satellites of Jupiter. Io, Europa, Ganymede, and Callisto, the four biggest moons of Jupiter. He saw them all with his telescope. And they were the first astronomical objects observed that rotated around a body other than the Earth. And so you can imagine. I mean, he made these really, really great discoveries in astronomy, which I think was fantastic. Unfortunately, he got convicted by the church because the church felt threatened by him because his observations contradicted their dogma that the Earth was the center of the universe, and so they had him. Ultimately, had him under house arrest in 1633. Spent the last 9 years of his life not being able to leave his home. And he also had all his books confiscated. He was forced to recant all of his theories, which I think was a really, really horrible thing. But Fortunately, it didn't last. I mean, other scientists verified, and I think his work was rediscovered. And another thing I should mention about all this, like I've said in many videos I've made before, I'm not at all a fan of mainstream religion. I hate organized religion. A big reason for it is because of what the church did to Galileo. And another thing I learned is that the church didn't even apologize for convicting Galileo until 1969. That was the same year we landed on the moon. I guess they withheld, they held on to their dogma as long as they possibly could, as long as they could brainwash enough of their congregation to believe in their geocentric theory, which in their view supported the Bible. As long as they could do that, they did, until it was obvious to everybody that the geocentric model was wrong. Once we went to the moon, once people saw pictures of the moon up close and the craters on it, and Neil Armstrong walking on the surface of the moon, they couldn't deny anymore that Galileo was right. So, pretty horrible thing, I think. I don't know, but I hate dogma. Einstein did too. Uh, you know, I mean, I don't want to knock religion too much because, I know religion's up for interpretation, and, I think it should be a personal thing, and I'm sure there's a lot of great things in Christianity. If you kind of take it metaphorically, I'm sure it says a lot about how to be a good person and live a good life. And if Jesus helps you do that, if God and Jesus and the Father and Son and the Holy Spirit help you do all that good, then the kudos to you. But, I don't really need that myself. So enough about that. But anyway, that was the telescope. And number three, the steam engine. I don't think any of us can deny this was a great invention. And it was ultimately the invention that led to the Industrial Revolution. But the reason I'm putting this as a Renaissance invention here is because the first steam engine was built in 1712. This does fall within the time period I'm defining as the Renaissance, 1500 to 1749. And the first steam engine was built by an Englishman named Newcomen, Thomas Newcomen. And his was also called the atmospheric engine. And it was a useful engine. I mean, it was a steam engine, and here's a diagram of it on the right. And the way it worked was you had a little furnace on the bottom right. You had a fire that heated this big tank of water. It boiled the water, and then once the water started boiling, the steam that came out of it would raise this. The thing on top, the part on the right, marked D. This is a little, I don't know what you call that thing, a little gavel or whatever, thing that rocks back and forth like a seesaw. It would raise the part on the right, and then the part on the left would go down, and the part on the left that went down would push this device on the left that would push down this water pipe, and then it kind of created a cycle. The water pipe would feed more water the big vat of water. It'd be marked B, so the whole cycle would continue, and this thing would generate power. But it was just used to power a home, basically, and heat a home. It wasn't used it didn't have a major industrial application. That came later. That came with James Watt. I mean, it was really James Watt's steam engine, which he didn't patent until 1769, that pretty much ushered in the Industrial Revolution, allowed for all this mechanization of industry via steam power. But obviously, steam engines were very important, and that's why I listed as number three. And number two. Now I'm getting to number two and number one. I think I should tell you. I'm not going to tell you what number one is yet. But number two is an abstract invention. It's not an invention of a physical object, but I think it was really a major invention, and so major, in fact, that I put it as number two, and that's calculus. And calculus, I think that was one of the greatest innovations, if not the greatest, but certainly one of the greatest innovations in all mathematics. I mean, it revolutionized math. Where would we be without calculus? I mean, calculus is pretty much the basis for all modern science. I don't think any branch of modern science could exist without calculus. It requires calculus and its calculations, at least in statistics. I mean, calculus is kind of the basis for statistical analysis, like the bell curve. The derivation of the form of the bell curve requires calculus. And there's a lot of other stuff. I think every area of science involves math that uses calculus, especially the hard sciences like physics. I think physics is the hardest science and closest to pure math. And you see calculus all over the place in physics. I mean, it's just about the only math that anybody uses in physics. It all involves calculus, at the very least. A lot of other very advanced math too, like linear algebra and group theory, and I don't want to get into all that, but it all requires calculus at the very basic stage. So that's why whenever anybody who's going into STEM fields, STEM meaning science, technology, engineering, and math, they're all required to learn calculus. And I think at least 2 years of calculus. In the first year of calculus, so standard first year calculus, which is usually 2 semesters, that involves the two major areas of calculus that were first invented by Isaac Newton and Gottfried Leibniz. These were the two guys who independently invented calculus. So there's two types of calculus they invented. Differential calculus, which is the calculus of small quantities, how things vary, rates of change. And then there's another type of calculus called integral calculus, which involves things like areas, that's what's called integration, figuring out areas under curves, defined by various functions, areas or volumes, or you can even do more fancy stuff like moments and all this other stuff. So calculus is extremely useful, and like I said, modern science relies on calculus, which is why I put it at number 2 on my list. And this picture on the right shows the 5 most basic rules of differential calculus, in case you're interested. And one thing, there's a lot I could say about calculus. Probably the greatest ancient mathematician that I know of was Archimedes. Archimedes almost invented calculus. I mean, he came up with what's called the method of exhaustion. He was able to compute pi, the ratio of a circumference to the diameter of a circle, which is approximately 3.14. He made the first kind of precise calculation of pi, and the way he did it was he used a method known as the method of exhaustion, which involved approximating a circle by a polygon with a lot of sides. I think he used polygons with 48 and 96 sides. He even came up with a formula that allowed you to calculate the area of a regular polygon with 2 n sides instead of the regular polygon with n sides. He could have used calculus. He could have taken the limit as n went to infinity and came up with an exact formula for pi, but he didn't do that. And the reason he didn't do that is because he and nobody else at the time understood the whole concept of infinity. That was one thing that was really missing with ancient Greeks. They came very close, but the ancient Greeks, they didn't have zero either. I think this was a big problem for the ancient Greeks. They didn't have zero and they didn't have infinity. And they didn't understand the concept of a limit. Because it's kind of hard to understand limits if you don't understand zero and infinity. Limits are things that go to infinity or that go to zero. You have to have either infinite quantities or infinitesimal quantities, which is what calculus relies on. And the genius of Newton and Leibniz was to make you have to, and anything in math has to be very, very precisely defined. That's the only way math works. Math relies on logic. So you have to define your assumptions of your mathematical framework. In this case, calculus. You have to define, in this case of calculus, you have to define what are called infinitesimal quantities, like dx. And that was a pretty difficult thing. It's difficult conceptually. But Newton and Leibniz were both able to do that. They came up with these epsilon delta proofs of limits, and so using those proofs, you can precisely define what you mean by derivative and an integral. And then you can do these amazing calculations that involve limits, limits of things going to zero and things going to infinity. And with that, with those tools, you can do some really, really amazing calculations. Like you can calculate pi exactly. Or you can do other really amazing things. You can calculate areas on parabolas or under catenaries or whatever kind of functions you can imagine. And that became the basis for physics first, and then a lot of other modern science. So you can't. I mean, I can't underestimate the importance of calculus. And one more thing I think I want to say about this. I didn't say this on the slide, but Newton, even though I think Isaac Newton was probably the greatest scientist of all time, one of the greatest intellectuals of all time, I think he was also kind of an asshole. I mean, Leibniz. Actually, nowadays I think most people think Leibniz. Like I said, Newton and Leibniz both invented calculus independently, but most people say Leibniz's version of calculus was superior. His notation was superior to Newton's. I mean, it was Leibniz that used a ddx, like dy dx. Newton called his calculus fluxions. He used the prime notation. Y prime of x, f prime of x, f double prime for derivative, double prime for second derivative. I think most calculus students learn both notations. They learn both Newton's and Leibniz's notation because they're both really widely used. But I think Leibniz notation is a little more intuitive, and it's easier to prove things like the chain rule. The chain rule makes a lot more sense in Leibniz's notation than in Newton's notation. Uh, most people consider Leibniz's version of calculus superior to Newton's, but Leibniz came up with his I think 6 years after Newton, 1671, whereas Newton came up with it 1665. But they were living in different countries. I mean, Newton lived in England and Leibniz lived in Germany, and they were separated by several hundred miles, and they hadn't communicated with each other. And Leibniz just happened to discover calculus on his own. And Newton got in a big fight with him about it. Newton claimed priority of discovery, even though Leibniz had discovered it independently of him. Newton, just got really, really pissed at Leibniz for claiming that he discovered calculus. They had a big battle, and Newton won the battle. I guess Newton got all the credit at the time for discovering calculus, for inventing calculus, and pretty unfortunate because Leibniz did some pretty great work as well. But anyway, yeah. Anyway, now I'm coming up to what I consider the most important invention of the Renaissance, and it's another abstract one, and it's the scientific method. I mean, I think this is the invention that really set apart the Renaissance from any earlier period in our history. I mean, think about it. Scientific method is basically it's the way we do science. It's the way we do modern science. And I think anything that people were doing before the scientific method, and by the way, it was a guy named Francis Bacon, an English statesman named Francis Bacon, who first outlined the scientific method. I don't think we know the exact year. It was around 1620. And I guess first I'll just describe how it works. I wrote it down on the slide, but I might as well talk about it. So what do? Here's the scientific method. This is usually what they teach, kids when they're teaching about science these days. So you make an observation, and maybe I should start with a simple example like gravity. I mean, think about Galileo. I like to use him as an example. So Galileo made a bunch of observations of things falling, like they say that he dropped two stones of different weights off the top of the Tower of Pisa. I don't think he really did that, but he did know that objects fell at the same rate regardless of their weight, their size. At least in the when you neglect air resistance or friction, he did observe this, and then based on that, he asked a question. Well, the first thing he did, he just observed things fall. Then he could ask a question like, how fast do things fall? And of course, you have to be very quantitative about that. But Galileo did and then he did some experiments. So he would roll objects down inclined planes, and he timed them the best he knew how. They didn't have very accurate time measuring devices. I think he used his pulse, but he kind of determined how fast different objects rolled down inclined planes. He discovered that they didn't roll at the same speed they accelerated. So he was able to, make some very important observations, to answer this questions by doing this experiment. And he came up with a hypothesis, and I guess his hypothesis, was first something like, the law of falling bodies, V equals GT. The speed of a falling object is a constant known as little g. The acceleration due to gravity, which is now about 9.8 meters per second squared, and then t is the amount of time it's been falling. So that was his, I guess, his conclusion after he did all these experiments. That became his theory, or his law, the law of falling bodies. And then, once he came up with that law, he could publish it. I think he did publish it. I don't know if that's one of the things the church confiscated from him. It probably was. But, that's ideally how science should work. And then sometimes you go down the wrong path. Sometimes you come up with a hypothesis that's just not true. And then you can do an experiment that falsifies it, that refutes your hypothesis. When that happens, you have to go back to the drawing board, as they say. You have to, change your hypothesis because, your original hypothesis didn't work. You change it a little bit, and this can be very painstaking. I mean, Thomas Edison had a famous quote about this. He said, "Genius is 1% inspiration, 99% perspiration." So, most of the scientific method involves a lot of perspiration. You make a lot of wrong guesses, but eventually you get it right, and then you come up with a theory that is verified by all the experiments that you do. And the more experiments you do, this is what's known as scientific induction. The more experimental evidence you have that verifies your theory, the more credence you have on your theory. And eventually, once you're confident enough that your theory is true, you publish it. And then once you publish your results, other people can read your results, other scientists, and they can improve on your results, or they can, I guess there's sort of two ways you can proceed here. You can either, if they're theoretical scientists, they can, add to the theory, look at different conditions, try to come up with a bigger theory that includes more facts, or they can maybe apply the theory, figure out a way to use it. That's applied science. So that's kind of how science works and how it's built up. And I think, this is the basis for modern science. And I think ultimately it's the reason why, we've had so many scientific advances in our modern society because of this method. And this is one thing that the ancients didn't have. And they didn't even think of doing experiments. Most of them didn't. A few of them did, like Eratosthenes. He did a really amazing experiment where he measured the size of the Earth, which unfortunately got lost during the Middle Ages. People still thought the Earth was flat in the Middle Ages, and they had these horrible TO maps. And Columbus had enough insight to realize the Earth was round, but he got the size completely wrong and thought he ended up in India when he was really in the New World. So and another thing I think I want to say about this scientific method. I mean, it's a really nice method, obviously, but it doesn't work like this in practice most of the time, unfortunately. And the reason it doesn't is because it doesn't take into account, what Hal said in 2001, human error. I mean, we're very imperfect beings, we humans, and we have a lot of human failings. We have a lot of jealousy and prejudice, and that's why we convicted Galileo, and not just Galileo. There've been a number of other tragic figures in the history of science. I can think of several of them. Darwin, Darwin himself was really embarrassed to publish his theory of evolution by natural selection because he knew it contradicted the Bible. He knew it contradicted the story of creation, but he did eventually publish it. And of course, he got attacked for that. Not only did he get attacked, but his theory got completely misinterpreted. Environmental determinism and social Darwinism, which were two horribly racist theories that were very popular in England because they made the English and the wasps look superior to everybody else. That was a terrible form of prejudice. And a lot of times scientific theories can get turned into horrible dogmas. In the case of the two cases I mentioned, social Darwinism ultimately got turned into eugenics and ultimately became the basis for fascism in Nazi Germany. So, a lot of bad things can be happen in the name of science. And there were some other tragic figures. I don't know many of you guys are familiar with Ludwig Boltzmann. Boltzmann ended up killing himself because he couldn't get the scientific community to believe in atoms and molecules. His theory, he had an amazing theory called statistical mechanics, which is kind of a mathematical basis for the kind of empirical laws of thermodynamics that were discovered in the mid 19th century. But it relied on the existence of atoms and molecules, which there was already a lot of kind of indirect evidence for. But the leading scientists at the time didn't want to believe in atoms and molecules, and so they wouldn't publish this theory. And as a result, he ended up committing suicide, which I think is a really horrible thing. And a lot of other scientists have had tragic lives too, like I can think of a couple others. Nikolai Tesla. He didn't kill himself, but he got used very badly by General Electric. He uh, he helped them with a lot of his theories of electricity. He came up with some pretty amazing applications of electricity and magnetism, but he didn't really get credit for them. He ended up basically homeless in New York City. And a lot of other tragic figures in the history of science, which unfortunately were casualties due to the fact that people in the real world weren't really adhering to the scientific method the way it should be adhered to. Anyway, I hope none of this happens to me. I've already had a rough enough life already. I don't think any of us will, but I just thought I'd point some of that out. But anyway, yeah, that's a scientific method, and that's why I think it was the number one invention of the Renaissance. And that completes my video for tonight on the what I consider the 20 greatest inventions of the Renaissance. Thank you for watching. Keep thinking, and I'll see you guys next time. Bye.